Hi guys, Sajad Hussain again with a new video. In this video, I am going to discuss the Building Code of Pakistan's new version, which is 2021. And I will take the same example which you can see on the screen, my previous video, which I will share. The link I will share on my description. Actually, my previous video was to design a building, 12-story building, as per the Building Code of Pakistan 2007. And as I mentioned before, that the Building Code of Pakistan 2007 was based on UBC 97. But now we have a new code, that is Building Code of Pakistan 2021, which is based on ASCE 716. So I will design the same building, and I will design the building as per UBC, BCP 2021. So let's just start. As usual, you know, this example I took from ACI, the PCA note on ACI 31899, and this was basically an example given on this page, and you can see in my previous video the example was calculation of seismic forces for a 12-story frame shear wall building and its component. So the same example I took, but this time I am not using UBC 97 and the seismic zones, etc. Rather, I am using ASCE 716. So the same example I took from here, and I prepared my load calculation in MathCAD. So you can see the building is the same, and now I'm considering Pakistan Building Code 2021, which is the same as ASC 716. Site conditions, I consider that this building is assumed to be in Islamabad. Why I took Islamabad? Because Islamabad is lying in lower limbs of Himalayas. In lower limb of Himalayas, they have the seismic activity, and of course, Himalayas have the seismic activity. So before Pakistan Building Code UBC 2007 considered this as seismic zone 2B. Uh, in fact, I have some reservation on that, because UBC 97 actually considered Islamabad and Karachi both as seismic zone 4. So there was a big difference between seismic zone 4 and seismic zone 2B. Anyway, now I assume the same building in Islamabad, and now I have considered the seismic data as per ASC 7 2021. Sorry, ASC 7 2016. As you know, in 2016 there are two major changes. Number one, the wind load is also an ultimate load now, and of course, the seismic conditions are totally different than UBC 97. So, as per our Pakistan Building Code, the basic wind velocity is 100 miles, and we should consider in Islamabad the category C, which should be considered. In earthquake data design, in the design for the earthquake data which should be considered in design, that site class should be D, importance factor should be 1, and the factors SS and S1, they are equal to SS is 1.2295 and S1 is equal to 0.3708. From where I took these values? Actually, if I open this Building Code of Pakistan 2021, I'll show you that in Building Code of Pakistan, when we define the earthquake loads, basically they have given the figures. For example, this is S1, SS and S1, but these are not tabulated. So that means one has to figure it out from these figures and the values of S1 and SS given here in color code scheme. I was not very comfortable with this scheme. Actually, what I suppose that they should have included the table where specifically these values should be tabulated, whether in Islamabad, what should be the value of SS and S1, and all the big cities like in Karachi, Quetta, Peshawar, Lahore, everything. Then I found that one gentleman, Fawad Najm, he is one of the contributors of the code. He has the website and he has tabulated these values. And I'll go to the table. Islamabad is not there, so I took Rawalpindi because Islamabad and Rawalpindi they are twin cities. So in Rawalpindi, the SS value is 1.2295 and S1 is 0.3708. So I took these two values and I plugged in here SS as 1.2295 and S1 is equals to 0.3708. The site coefficient as per the table FA is 1.008 and FV is equals to 1.929. You can check these values from the table, but further details are there. Of course, the material is F-C is 4000 and unit, the concrete unit weight is 145 or 150, you can say, pound per cubic feet, etc. So these are the standard values, no need to change anything. But anyway, the important thing is the loads which are defined here. In my load calculation, as I mentioned, the dead load the dead load is calculated like this, the weight of the slab, etc. And this load has already been provided in my STAD model, which is here. So in STAD model, this model is the same as the previous model. So all the vertical loads are the same. No need to change those vertical loads. So you can see the dead load as I calculated before, it's the same. Live load, as per the example given, these are the live load. For the floor, this is 75 pound per square feet, and for the roof, it is 20 pound per square feet. Then I calculated wind load. As I mentioned in Building Code of Pakistan 2021, it's section 1603. It says that the wind velocity should be considered as 100 mile per hour, which is equal to 44.704 meters per second. Importance factor 1, kz should be equals to 1, kzt is equals to 1. All the cross references are provided over here. Kd should be 0.85, but I took 1. The gust factor is 0.85 and the velocity pressure is, as per the formula, the velocity pressure comes out to be 25.6 pound per square feet. And for the main wind force resisting system, the load is applied as per the equation P is equals to Q times GCP minus QI into GCP. And I use the wind generator of STAD and I applied the load. I will explain how it is done. Seismic load, as I mentioned here, SS is equals to 1.2295, S1 is equals to 0.3078. And the site class D should be considered as per BCP 2021. The value of FA and FV as per the table 11.4.1, the value interpolated comes out to be 1.008 for FA, and for FV the value comes out to be 1.929. Very simple. Then I calculated the SMS, SM1, SDS, SD1, the time period T naught, which is as per the formula, it comes out to be 0.115. The short period, transition period TS is equals to 0.57. The long period I took as 12 seconds. Some people take it as 8 seconds, some people take it as 12 seconds. So it does not make any big difference if you consider as 8 seconds or 12 seconds. The coefficient for calculating the upper limit for the period, the CU is here, and to calculate the time period, the value of CT and X as per the table 12.8-2 of ASCE 716. These values are here, and I took CU is equals to 1.4. The height of the building is 148 feet. CT comes out to be 0.016. That means this is concrete moment resisting frames. So CT is 0.016 and coefficient X is equals to 0.09. So the fundamental time period comes out to be 1.437 seconds. The maximum value of T comes out to be 2.011 seconds. Based on all this data, I calculated the spectrum, and a spectrum is produced. This design responsive spectrum is produced here. The value of the SA is called design responsive spectrum acceleration. This is based on risk targeted maximum considered earthquake, that is MCER. So MCER response spectrum can be calculated with this formula, where MCER is 0.498. Importance factor is I, and the importance factor is given in table 11.5-1. Having all these values, I tried to evaluate the seismic design category. So the seismic design category based on short period response, that is, if SDS is equals to 0.826, then the seismic design category based on SDS is D, and similarly the seismic design category based on SD1 comes out to be D also. So it is confirmed that the seismic design category for this structure is D. That means in Islamabad or even in Karachi, the seismic design category will be D. So one has to be very careful, because if the structure falls in seismic design category D, then there are special requirements and we have to evaluate all the requirements. So I'm going further down and I'll explain the requirements for seismic design category D and what evaluation or what parameters I have considered. For example, what should be the analysis procedure? As mentioned in chapter 12 of ASCE 716, and table is 12.6-1, the permitted analytical procedures are: if the structure has no structural irregularities and not exceeding 160 feet in structural height, then equivalent lateral force procedure as explained in 12.8 is allowed. Although you can go for modal responsive spectrum analysis or nonlinear response history procedure, which is given in section 12.9 and chapter 16, etc. These are permitted, but we will go for this simplest one, that is equivalent lateral force procedure, which is given in 12.8. So as per the procedure which is permitted, I am going further down. and I'll see that if this building is a special reinforced concrete moment frame, so the value of Ra, that is modification coefficient Ra, it should be 8. The overstrength factor omega should be 3, and deflection amplification factor CD should be equals to 5.5. Structural system limitation including structural height, the height limit, there is no limit. That means we can safely use these parameters. And all these tables are taken from ASCE 716, like this table is table 12.2-1. Similarly, in another direction where it is resisted by the shear wall, the values are 7, 2.5, and 5.5. Now, in north-south direction, what is north-south direction? If I'll show you, this is the north-south direction. That means in north-south direction, the shear wall, which are here, they should be considered in resisting the lateral forces. But in east-west direction, there is no shear wall. So in north-south direction, the response modification factor should be 8. Sorry. Now system overstrength factor should be 3 and amplification factor CD should be 5.5. Now we have to check irregularities. We have to identify types of horizontal irregularity. The types are 1A, 1B, 2, 3, 4, and 5. So 1A is torsional irregularity, 1B is extreme torsion irregularity, type 2 is re-entrant corner irregularity, number 3 diaphragm discontinuity irregularity, number 4 out of plane offset irregularity, and number 5 non-parallel system irregularity. Here in our case, none of the conditions are applicable, so we have not considered any action, we are not taking any action. This is not applicable. In horizontal cases, this building is a regular building. What about vertical irregularity? In vertical direction, there are irregularities 1A, 1B, 2, 3, 4, 5A, and 5B. 1A is stiffness, soft story irregularity. 1B stiffness, extreme soft story irregularity. Number 2 is weight or mass irregularities. Number 3 is vertical geometric irregularity. Number 4 in plane discontinuity in vertical direction. Number 5 is discontinuity in lateral strength. Number 5B discontinuity in lateral strength. Of course, you can check the details. But again, in vertical direction, we do not have any irregularity, so no action has been taken. Redundancy factor, as per paragraph 12.3.4.2, I took the value of rho is equals to 1.3. Equivalent is static analysis for seismic D structure is permitted as per table 12.6.1. Now seismic response coefficient CS is this much, and finally the CS comes out to be 0.041. Now here I want to mention one point. Now in north-south direction, uh, if we calculated this coefficient for base shear based on UBC 97, it was almost the same. It was I think 0.44, and I can say that although the base shear value is almost the same, so the value of base shear will not be much different as compared to if we compare both the codes, that means UBC 97 and ASC 7 to 16. That means if someone is designing a building in Islamabad or in Karachi based on Building Code of Pakistan 2007, and if someone is designing the same building with the new code, that is Building Code of Pakistan 2021, he will get almost same value of base shear. But then what is the difference? The difference here is in terms of detailing requirement. So not only you have to be very careful in evaluating the base shear, but also you have to think for the detailing requirements of the structure. So here I'll explain how I further calculated the structural weight. Of course, the slab, superimposed dead load, beams, etc., column, and total weight. That's the second to 11th story, and this is the ground floor. So all these values are calculated here, and then I distributed the seismic load in vertical direction in north and south direction. So this is the vertical distribution of base shear in north south direction. Of course, the vertical distribution is given by the equations are given by 12.8-11 and 12.8-12. This is from ASCE 716. So I tabulated all these values and calculated the base shear, which is I calculate the story shear, which is here. Like for example, what will be the at roof, 11, 10th, etc., etc. So this is the total value of the base shear distributed vertically. In east-west direction, as you know, I have taken RA is equals to 7, omega is 2.5. So the whole procedure is the same. It is just a replica of the north-south direction. And here the value comes out to be the coefficient for the base shear comes out to be 0.047. Again, it's almost same. So the base shear is in the same order, I can say, and vertical distribution in east-west direction, the same procedure is adopted over here. So that means the base shear value remains almost the same. But now there is a big but. We have to consider the effect of vertical seismic effect, EV. And the vertical seismic effect is zero point 0.2 into SDS into D, which is the dead load. And this is as per section 12.4.2.2. So here I just calculated the coefficient for EV, which comes out to be 0.165. Omega I have considered as 1.3, as I have mentioned before. Now we have to determine the applicability of orthogonal interaction effect. For seismic category D, as per section 12.5.4 of ASCE 716, orthogonal interaction effects are not required to be taken in consideration as per section 12.5.3. As because the building does not have horizontal irregularity of type 5. So this is very important. Now, horizontal distribution of seismic force effects. Of course, I have generated the seismic force by the load generator of StatPro. So it distributed the load by itself. So I did not do anything. So I left it for the software to be considered. Diaphragm flexibility. So as per the clause 12.3.1.2 ASC 716, the diaphragm considered is a rigid diaphragm. So I model in STAD this diaphragm as a rigid diaphragm. Inherent torsion for rigid diaphragm, of course, I consider 5%. This inherent torsion will be part of a STAD analysis based on mass lumping for seismic loading and actual stiffness model. Accidental torsion. So the accidental torsion is taken as 5%, which is a general rule, so nothing special. See, dynamic amplification of accidental torsion for rigid frame. Dynamic amplification for accidental torsion is not applicable in our case because there are no irregularities of type 1b, etc. Then designer of collector and courts. This is very important thing. As for the as from the figure 12-10 12.10-1, full length shear wall. That means if a shear wall extends from one end to another end, there's full length shear wall, no collector is required. But for example, there's a small shear wall, say for example like a stairwell, then the beam which are connecting the column and the shear wall, they are called collectors. So in our example, I have considered another load combination for collectors and the beams are checked against these loads. So the collector elements require load combination with over strength factor. This is very important for seismic design category C through F. So our seismic design category is D. So we have to consider over strength factor to design the collector elements. The P delta effect as per clause 12.8.7 ASC 716, we have to check whether P delta effect should be applied, it should be considered or not. Uh, I did not go into all these details and check everything, but I considered P delta because I know that in concrete structure it is better to perform P delta analysis. So as I have mentioned that P delta analysis has been performed by StatPro. Now for structural wall and their anchorage, structural wall and their anchorage shall be designed for a force normal to the surface equal to FOP, which is equal to 0.4 SDS times the weight of the structural wall. Actually, in this example, I am not designing the structural wall separately. So for the time being, I just left it as it is. Maybe in part 2 of this lecture, I'll design the structural wall and then I will consider the load as specified over here. The drift and deformation check, yes, this is done because for all other structure 0.02 times HE, so the drift is checked with this parameter and stat checks the drift and the limit is given as 0.02. So the detailing requirement, a special moment frame shall follow all requirements given in chapter 18 of ACI 31814. 19 and 14 they are the same. So all the detailing requirements should be fulfilled as per ACI 318. Of course, in Islamabad, rain is there. So I have considered as per Pakistan building code the rain which is 2 inch. So the load of rain is equals to 52.52 pound per square feet. Having all these loads and the information given there, I have considered these load cases. These are the primary load cases. For example, seismic load in X with 5% eccentricity. In negative direction, Z minus Z in X and minus X Z, and minus Z. So these are 8 seismic load cases. Ninth is the structure dead load, 10th is the floor live load, and the roof live load is taken as this. Rain, of course, load case number 12 is the rain load, and at the end I define the wind load in x direction, minus x direction, positive z direction, and minus z direction. So all these loads are defined in my model. I'll explain. And then load combination. This is very important. And my experience is that if you are using STAD, then you cannot generate the load combination based on the automatic load generator or automatic load combination generator, because there is vertical effect, etc. They are not considered properly. So it is always better check these conditions and then apply these combinations over here. For example, the basic load combination, equation number 1 to 5, they are the same. No issues over here. But when the seismic load is prescribed, then you have to consider load combination number 6 and number 7, where you have to have 1.2D plus EV plus EH plus L plus 0.2S. So all these factors are there, and with this, my equations, my load combination may become 1.365D plus EH plus L plus 0.2S, and the next one, the equation number 7 becomes 0.735 plus EH. For chords where the overextend factor should be considered, as per section 12.4.3, the load combination should be 1.2 plus EV plus EMH plus L plus 0.2S. And here EMH is omega times QE, where QE can be taken as the effect of base shear calculated above. So here basically it should be multiplied by omega, which is there. So what I have to do, I have to modify all my load combinations if I am generating it by load generator, or I have to input manually all the load combinations. So all the load combinations are tabulated over here, which are defined with rho and omega. So a lot of load combination is generated because of the seismic forces. So let's go back to the model. This model, as you can check it from my previous video, same model I have used. The shear wall is 18-inch thick, and the external columns are 22 by 22 inch. Internal all columns are, sorry, these are the beams which are 20 by 24, and internal columns are 26 by 26. Then loading. As I mentioned, I defined the wind load cases. So for wind load in positive x direction is there, same as wind load as per ASCE 716, intensity is there, and wind load cases are here. For example, the wind load in z direction, it will take little time. So here all the wind load is generated when wind is blowing in z direction, that is the wind load on the face of the structure. Windward load, this is the leeward, and these are the side, on the right hand side and on the left hand side. So same technique is used for minus z direction and plus x direction. It takes little time to generate all the forces. So if wind is in positive x direction, so this is the windward, leeward, sidewall, all. So these forces are already calculated. And for seismic conditions, I can say as per ASCE 716, all the values are provided over here, and weight, floor load, etc. All these values are provided over here, and all these 8 seismic loads are provided here. Now, with all these loading conditions, if I analyze, it will take little time, but anyway, the result is that I will use to design the beams and column, etc. I will use advanced concrete design module of STAD. For the beam, it's okay, but for the column, there are some problems. Let me show you first what happens if we design the beams. I'll just design beams of only one floor, and then we will see if there is any failure or anything needs to be changed. And secondly, I'll design the columns and we will check. Shear wall design is a very good question in STAD. Shear wall design is provided in advanced concrete design module. But the problem is it's a little bit tricky. So I prefer to design the shear wall manually, which I will cover in another lecture, but not here. And maybe I will develop one detailed lecture to design the shear wall in RCDC, that means Advanced Concrete Design of STAD module. Because you have to design, you have to define the wall in a different way. Here I just consider a simple four-noded element as shear wall as a concrete member of the concrete of quad element having thickness of 18 inch. But that is there for stiffness calculation, but not but the stat cannot design the shear wall. But if I use ETAB, so ETAB is better in this regard, I can say. ETAB can handle shear wall, and there are another parameters which can be designed like end element, etc. So if I'm given a choice to design a multi-story building, so in my opinion, I'll prefer ETABs because of the limitations provided over here. Maybe in some another lecture, I will give details that what are the limitations in STAD for defining the shear wall and how flexible is ETABs. Anyway, let's go to concrete design, RCDC. Here, message. So the project maybe 12. 12 story building. client XYZ, engineer MSH, and I'm designing as per ACI 31814. So the beams, maybe we can select, no, not the top roof beam, rather maybe the first floor beam. So typical beams are there. This is beam number one, beam number two, beam number three, beam number four, beam number five, six, seven, 8, 9, 10, 11, and 12. Of course, here beam number 11, these two beams should be designed as per over strength factor because they are the collector elements. Similarly, this beam and this beam, these should be designed for the load combination with over strength factor. Rest, let's check for the other beams. Here we will go general arrangement. Ignore torsion. No, we are not ignoring torsion. Ductile. Yes, we need the ductile design, and this is a special moment frame. French flange beam. No, for the time being, it's okay. Rest of the things are okay. We don't want to check the crack width now. Leave it as it is. C3. Okay, that's fine. Okay. Then rebar curtailment. I'll leave this to default. Detailing and drawing setting. Okay, no issues. I'll leave it as it is. Preferred bar spacing. I will not suggest anything, so leave it as it is. Basic load cases. So all the load cases are here. So we have to specify the load type. This is earthquake X, earthquake X, earthquake, sorry, Z, earthquake Z, seismic X, earthquake X, Z, and earthquake Z. This is our dead load, live load, roof, rain. This is wind in Z direction. This is also wind in Z direction, wind in X. This is also wind in X. I'll select all these load cases and I will transfer here. So all the primary load cases are defined. Now add from analysis. No, it's okay. Now here, since all the load cases are selected, so what I'll do, I'll select those load cases which do not consider the overstrength factor. That means my load cases are from 101 to 129. 101 to 129. But then from 130 to 137, these are for collected elements which I am not going to consider now. But then 138 to 149, these should be considered. And again 150 onward, these loads are for collector elements. So I will not consider this because here the overstrength factor is 3. Now, okay. Then I'll go to auto design. You can see here a green strip from top to bottom. That means no beam fails. All the beams are designed, so there is no issues. And in report, we can go to failure diagnostic, nothing. So that means beams are fine here, no issues. For example, if we want to see the design calculation, we can click over here. As an example, just one beam. So detailed design calculation is produced. You can check the applicability of the clauses in chapter 18. All the clauses are mentioned over here. So you can see a detailed design calculation is there. Now you can see the elevation and section. That's for only one beam. Okay. Now you can see the bars, elevation, section, etc. And you can see the proper detailing, everything is there. For any other beam, we can see, for example, beam number 12 or say beam number 1. So it will draw elevation, it should draw cross section, it should draw the cross beam, mark the anchorage, and this section mark should also be shown. So now you can see a very detailed drawing is prepared. The beam, reinforcement, all these reinforcement, column location, and the cross beams, they are also shown. These are the sections, stirrups, everything is there. But for these stirrups, you have to check that there should be a tie in the middle or not. Because these tools are our slaves. We should not be the slave of the software. As an engineer, you have to check each and everything before releasing the document for the construction. So here you have to check the bars, their spacing, and the requirement of stirrups, additional stirrups, whether it is there, it should be there or not. That I am leaving for the viewer. They should decide by themselves. I'm just trying to explain that how we can uh, easily use the software and we can generate the drawings. But be careful, the software is not an engineer. You are the engineer and you should know the limitations and the provisions. So before issuing the drawing blindly, please check Each and every detail should be checked. So we can save the file. It takes maybe a couple of minutes to go back to a STAD model. That means whether you are following UBC 97 or you are following ASCE 7 2016. That means in Building Code of Pakistan 2007 or you are following the new Building Code 2021, base shear will be the same. Beams, they appear to be same, but one has to check carefully. But now I'm going to check the columns. So again I will select RCDC, and this time 318M. Why I selected? Because in 318 2014, if I select, so the columns cannot be designed. So I have to select 318M column. So let's create the new project. Settings, design settings, of course, ductile design, special moment frame. Okay, uh, everything is there. Basic load, basic loads. Again, I have to define earthquake X, earthquake X. I have to define earthquake Z, earthquake in Z direction, earthquake X, earthquake X, earthquake Z, earthquake Z, then dead load, then live load, then the roof, live, rain, wind in Z, wind in Z, wind in X, wind in X, and select all the load cases. So it is there. Same thing. No, I don't want to do anything. So all the load cases are there as I did before. For the column also, I have to unselect load case number 130 to 138, and sorry, 138 to 149 I have to select. and unselect 152, 157. Okay. Now let's design. Now you can see column failure. These columns failed. Here the red line, it shows that these are the column failure. Why? Go to failure diagnostics. Failure type is mentioned over here. That means these columns do not qualify for even load and axial bending plus in detailing, etc. Some are failing because of the detailing. So that means I don't want to save. That means if you are designing a building, then you have to be very careful as per the new Seismic Code of Pakistan or ASCE 716. You have to be very careful for the columns and very careful for the detailing requirements. So this is my message for the engineers who are designing as per ASCE 716, that for God's sake, please be very careful when you are detailing the columns, and you should check each and every details. Thank you very much. Do not forget to subscribe my channel, and hopefully you will go through it. And if you have any comments, do not hesitate to write it, and hopefully I'll try to reply you as soon as possible. Bye.